Hello everybody, welcome to component-based software development. This week we'll keep introducing the different kind of component models. If you still remember, last week we present a taxonomy of component models. Right? There is 5 categories. Still remember that? Well, starting from this week, I will teach you, or I will show you the different kinds of the category component models in categories, in these categories. This week we start from category 1. Category 1 is design without repository. Still remember that? Yeah, we have a builder here, right? That repository here, but nothing in the repository. This is the assembler. Likewise, we don't have the assembler in category 1. However, this is runtime environment. Still remember, right? Okay, so we will give you 3 examples in category 1, including Acme-like ADLs, CML, UML 2.0, and finally Pickles. First is Acme. Acme actually is a kind of it's a classic ADL, kind of old. It starts in middle 1990s. Acme is a simple generic software architecture description language that can be used as a common interchange format for architecture design tools and or as a foundation for developing a new architecture design and analysis tools. Well, which means what? Actually, it says Acme is a prototype of ADLs. Yeah. Itself, of course, it is a ADL, and also it is a good idea, and it is extendable. So many other ADLs are actually developed based on Acme. So that's why we said it is a prototype of ADL. So this one, Acme, typifies first generation ADLs. The first generation ADLs, such as Darwin, Unico, Wright, and ArcJava. So Darwin and Unico may be very famous, but unfortunately, no one uses them anymore. ArcJava, people still using them. Sometimes with the Spring framework, we still using ArcJava because it has more. It has more powerful when we try to design a complex system. In Acme-like ADLs, a component is an architectural unit that represents a primary computation element and a data store of a system. So, yes, the component is an architectural unit because it is ADL, right? It's an architecture description language. So not only he has a computation element, but it also have a data store in the system. So in Acme or Acme-like ADLs, the interfaces are defined by set of ports. Each port identifies a point of interaction between the components and its environment, including other components. Therefore, a component may have multiple interfaces by using different types of ports. So now we know how it works if we want to compose to different ADL, different Acme components, right? In Acme-like ADLs, components are composed by connectors. We use a picture here to show the components, the connectors. The black dot is the components, is the connectors. So connectors connect components via their ports. So in this picture, the triangles are ports. This one are connectors. So connectors are ports. They are not the same thing. Okay. In Acme, like ADLs, the components and the system are designed together in an ADL tools. Therefore, the builder is the ADL tool, if any, right? There is no repository, there is no assembler, but the builder, we have it. It is the ADL tool, and the builder we can do components and the system. We can design components and the system inside the ADL tool. Hence, in Acme like ADLs, we can use a picture. We can use a picture to express its form, right? So the builder here, we have a component A, component B, component B1, B2. C here is the connectors. Therefore, after we design the system in the builder, we directly send them into the runtime environment to execute. So in runtime environment, this one A prime, it is the implementation of the A. B prime is the implementation of B. Well, similarly, B1, B2, they are implementations of B1, B2, respectively. Notably, the C prime, it is the implementation of C. So the connector is actually something, it's an object. Right? So when we use a connector to design something in builder, we have to implement this connector as well in runtime environment. So the component lifecycle coincides with system lifecycle because, as we showed before, there is only builder and the runtime environment. So the component lifecycle coincides with system lifecycle. And during the component or system design phase, components are identified and defined, and the components are composed by connectors into a system design. So the design for both components and the system has to be implemented somehow in a chosen programming language. At runtime, the implemented system is executed in the runtime environment of that programming language. What does that mean? The last two sentences, what does that mean? Right? Because ADL, Acme like ADLs, usually, well, it is, like I said, it's a language for architecture description, right? Used to design architecture. It is not a programming language. This language is usually extended from a programming language. So it is not a programming language itself. Therefore, for example, ArcJava, he has a Java here, so we know it is a Java-based language, right? He has all the semantics, syntax of Java. We only give him more grammar so we can use it to design architecture, but in the end we still use a Java compiler, right, to compile it, to run it. That's why we said at the runtime the implemented system is executed in the runtime environment of that programming language. If we use ArcJava here, Acme or ArcJava, this is the blue background, shows it is the builder, right? In builder, we design a system like this using ArcJava. Then, in the runtime environment, we actually execute this system in Java, right? So this is Acme like ADLs. Now we should Acme example here. We should consider a simple bank system consisting of an ATM component and a bank consortium component and the two bank components, bank 1 and bank 2. So how we define this object? So we defined it using keyword component ATM. It has a pot stand, and this one, component bank consortium, has two ports: port receive, port send. Component bank 1 have a port receive, and also he have a property bank ID to show this is bank 1. Also this one have a port receive, and the bank ID should show this object is bank 2. So in the design phase, the architecture for the whole system is designed like this. The ATM uses port and the connector to connect bank consortium, and this one using his ports and the connector to connect B1 and the B2. Using the above components and the following connectors, we have to define the connectors as well. So the connector ATM to BankCon, which has a role called request and another role called produce, and the connector BankCon to Bank 1, BankCon to Bank 2 also have two roles, a request and a produce. Okay. Then, therefore, the final, the pseudo code, and it's not the pseudo, it's the real code here. The code is like this. The system, also a keyword, bank system, it has component ATM, component bank 1, and the component bank consortium, component bank 2, and the 3 connectors to connect them. Then finally, we have something called attachments. These attachments to show is to allow you to bind these porters, to bind these porters with the connectors. It is the actual activity of the connecting. Also in the attachment, for example, at ATM.send, this is his port, right? To ATM to BankCon.request to a connector, a port linked to a connector, and this connector links to another port of another component. See, port, connector, same connector to another port. See, so this is how we use Acme. Not only have the component, we have to define the connectors very carefully. The port and connectors very carefully. So this is the example of Acme. Now I show you another language belonging to category 1, which is UML 2.0. This one, maybe you familiar this one a lot better than Acme. In UML 2.0, a component is a modular unit of a system with well-defined interfaces that is replaceable within its environment. So here, a component, we call it a modular unit of a system, because we know UML. What is UML? A unified modeling language. So here's a language to design a model. So of course, in a model, every component is a modular unit. It is a component model, and every component is modular unit. Component defines its behavior by required and provided interfaces. So these interfaces are ports, right? Just like the ports in Acme. And the services of components. What is the services? The services of components are encapsulated through their required and provided interfaces. Okay. So I still give you examples to show you how to understand the definition of interfaces in the services here. So UML 2.0 components are composed by UML connectors. There is two kinds of connectors: delegation connectors, assembly connectors. See, this is the delegation connectors. This one, the arrow here, actually this one, and assembly connectors. This one, the lollipop with a half circle. This one. composite assembly by the assembled by the assembly connectors. So this component, they are assembled by this assembly connectors. Systems are assembled by delegation and assembly connections, which means, for example, if this one is a system, right? If this one is a system, the components, subcomponents inside the system, we're using a delegation connector to connect the interface of this system and the interface from its subcomponents. So this activity we call it delegation. Okay, so this is a delegation connectors for. Also use assembly connectors, which means a system can compose with another system. Between the two systems, we're still using assembly connectors. So in UML 2.0, the components and the system are designed together in a visual builder tool, such as Visual UML. We have now we have a lot of UML tools, right? UML tools. For example, there are too many examples. Visual, right? Microsoft Visual, and you can even use Visual Studio to do that. Very convenient. So the Visual Builder tools is the builder. So because UML components, we actually don't have any executable code inside the component, right? It's just drawing some blocks, drawing something. So we only need a visual builder, a visual tool to draw the pictures. So the visual builder tool is the builder. Of course, there is no repository and there is no assembler. And in the runtime, the runtime is the implementation language runtime environment. The A here, the UML component A, finally becomes the UML A instance, and B, and the instance B is a UML B becomes UML B instance, and this one is the connector. So now you can understand. I think now we can understand what is implementation language runtime environment, right? For example, if I using C#, we're using UML to design the architecture, and using C# to implement this architecture, to realize the designing. So here becomes what? A C#, right? This is UML. So here C# is the implementation language. Yes, this is how we using UML 2.0, and that's why UML 2.0 belong to a category 1. So let's see his component life cycle. Also, it coincides with the system life cycle. And during the component system design phase, components are identified and defined, and the components are composed by connectors into a system design. So the design for both components and the system has to be implemented somehow in a chosen programming language. At runtime, the implement system is executed in the runtime environment of that programming language. So just like Acme, and Acme like ADLs. Okay. We still give you an example, the same example of the bank system. So consider a simple bank system that is implemented by ADM, Bank Consortium, Bank 1, and Bank 2 components. Okay, now let's see the 4 components of ATM, Bank Consortium, Bank 1, and Bank 2. This is a very classic UML object, right? UML class. We have a class name, we have the prototype, and we define the interfaces. For example, the ATM, get card number, check bank ID, and the Bank Consortium, check bank ID becomes the provided interfaces. And its required interfaces is get card number, withdraw, deposit, check balance, something the customer will want to do, right? And the component back one, see his provided interfaces, withdraw, deposit, check balance. So now we have the components. Let's see the systems here. This is the systems. ATM and the bank consortium, they are linked by what? Interfaces, right? And the bank consortium links with bank 1, bank 2 with interfaces 2. So in design time, the architecture for the whole system is designed, which means in design time, the output of design phase, it should be like this. Then, based on that, we're using a language, C#, Java, Python, whatever, to realize this picture. Okay, so we don't give the code of this one because you can use any programming language to realize UML. So all you need is to how to do the design in design phase using UML 2.0. Okay, next one we call it PECOS. PECOS, I guess most of you don't familiar with this one. PECOS component model, right? In PECOS, a component is a unit of design which has a specification and implementation. Right? So, likewise, he is a unit of design. Before we call in Acme, we said a component is an architectural unit. In UML, we call it a modular unit. In PECOS, we just give them the name a unit of design because it's a little hard to define what kind of unit it is. So we just call it a unit of design. However, this unit has a specification and implementation. So which means one, every component has a name, a number of property bundles, a set of ports, and a behavior. Two, the ports are interfaces of the components. So PECOS components are specified in the COCO language. COCO language is component composition language. We call it COCO language. So we give a small example of the PECOS component. Right, this one we're using this picture to show is PECOS. Yeah, we have the components here, we have ports here. So in PECOS, components are composed by connectors, and the connectors connect components via their ports. So inside this system, what's the connectors? Where is the connectors? This is ports, right? This is the ports. The brown circle is the ports. So what's the connector? Yeah, the line. The line itself is connector. It connects the components via the ports. So in this example, we see a device, active component period to 1000 milliseconds, clock milliseconds, display time, digital display, time in milliseconds, and event loop, active components. Right? Started, control something. So in PECOS, the components and the system are designed and constructed together in a programming language, a programming environment such as Eclipse. So, which is very similar, like Acme or ArcJava. We can using a builder such as Eclipse to design and construct together, right, to do the components as system. So here we have the A components in the builder system, and the system A compose B. This is a system, yeah, in the builder as well. And no repository, no assembler, directly something we design here is sent to runtime environment. Also with this is implementation language runtime environment. Instance A is PECOS A instance, is PECOS B instance, and finally we have a connector. So the programming environment is the builder, as we said, no repository, no assembler, everything just into the runtime environment. So component lifecycle coincides with system lifecycle. So this one tackles component lifecycle, just like Acme and UML 2.0. And during the component system design time, components are identified and defined, and composed by connectors into a system design in the COCO language. The design has to be implemented in a chosen programming language, usually Java or C++. At runtime, the implemented system is executed in the runtime environment of Java or C++, which means Pecos, just like UML, is focused on the designing, focus on designing, constructing. So if you want to realize something, a design, a system design or component design, we have to use some programming language, finally as Java or C++. So here is the example. Consider device assembled from clock, display, event loop, and digital display components. So component clock, we're using a keyword component here. The output is a long data type millisecond. Component display's input is a long data type time. Active component event loop, output boolean started. And finally, component digital displayer. It has two inputs, long, the first one is a long data type, time in millisecond. The second one is a boolean control. So finally, we can link them here in the design phase. The architecture for the device is designed like this. Okay, it's designed like this. Also, we're using active component device. This is the system. Inside this is the system. We connect all the components. First, we also declare all the components: clock, display, digital display, event loop. Then we use a connector to connect them. Connector time, clock milliseconds, displays time, and the digital display time in milliseconds. This one is a connector. Second connector, the event loop started. This one. We connect the port event loop dot started, and another port can store from digital display. So looks still very easy to use, right? Yeah. Okay, thank you very much. This is lecture 5.